So we're going to continue discussing chapter 12, and we talked about ways to increase reaction rates and all of that relating back to how to get a prom date. So keep those in mind when we go through this, but how do we know what the reaction rate is of a particular reaction? And then we would use one of our five ideas that we talked about of how to increase it after that. So I guess we have to talk about how to determine the reaction rate in the first place, so then we can apply our newfound knowledge of how to get a prom date to that. So reaction rate is how fast a reaction is taking place, and the equation is taking a look at the concentration or molarity of a reactant or product per unit of time. So rate, reaction rate, or just simply rate, is the concentration of A at a certain time minus the concentration of A at another time over the times, those two, the actual times subtracted as well. So you have this change in concentration over time. And if you guys remember from last chapter, what is concentration measured in? It's molarity, so moles per liter. So A is the reactant or product that you're being considered, and T is usually in seconds. So I'm going to just kind of go back really quick and have you look at this, and you can see, so rate is moles per liter second, which that moles per liter, if you remember, is molarity. So simply written, it's molarity per second. How do you determine that? Well, it is something, you need something to measure that rate, and it is determined by whatever is easiest to see or measure. So like they might look at a color change, if you could collect the product like a gas, or if they could measure the pH change. It varies. So whatever is easiest to measure in a reaction is what they're going to measure to determine the rate. We're going to take a look at, for example, this reaction here. You have 2 nitrogen dioxide decomposing into 2 nitrogen monoxide plus oxygen. And if you were to look at the coefficients here, you have 2 to 2 to 1. And if you're talking about at time equals 0, and let's just say that we had 0.01 molarity of this compound, you would assume that you'd have 0 of this and 0 of this, and you would let the reaction take place. What you should see is that over time, this concentration of your reactant should go down, and these two should go up. What you also have to think about is the relationship, the stoichiometry, the 2 to 1 relationship, that this will start to be created in a much faster, see in looking at the graph, a much faster molarity than the oxygen, is about half as much. What's interesting is you're going to get a curved line for these, and I'm just going to go back to this page. And what we want to look at is maybe a common question, and this you see this question often on the AP exam, is they might give you, say, a rate of one of these and ask you what is the rate of one of these appearing. And that is simple stoichiometry when we look at that. But before we do that, I'm just going to show you kind of time equals 0. Here's your initial concentration of your reactant, and these are 0 and 0. And over time, every like 50 seconds, say, they're taking the new concentration and jotting it down, and you're going to see that this is appearing approximately twice as much as your oxygen is appearing. And so here's that, let's just say we knew that the rate in the previous example to be 3.2 times 10 to the third molarity of oxygen is being created every second. How would you be able to determine the rate of the disappearance of NO2? And because you know the rate of 1 and you have a balanced equation, you can actually just do this using your simple stoichiometry that you've done in the past. And I'm going to just show you, because I can't write on anything, I'm just going to show you quickly that this is simply, if rate is 3.2 times 10 to the negative third molarity per second of oxygen, then we're going to use stoichiometry to determine the rate of disappearance of the nitrogen dioxide. write down the rate of your oxygen, use the coefficients, it's a 1:2 ratio determined from the balanced equation, and you should get approximately 6.1 times 10 to the minus third molarity per second. And so those can be very simple stoichiometry type problems, and they will most likely ask you those. I've seen those in the past. What if they don't give you those ideas? What if they don't give you the rates of things? And so that's where we're headed into what we call two different types of rate laws. One's called the differential rate law, or just a lot of the time they just call it rate law. And they mean this. And it shows how the rate of a reaction depends on concentrations. And if for you guys that are looking back at, here would be that graph, and here it's going over time. They're measuring the concentrations over time. And how would you get the rate from this? Well, it's easy to get the rate of a straight line because you could take the slope of that. But if it's curving like this, you have to do something a little different, because at each of these different pieces, it changes. So those of you that are in calculus, you probably might be thinking to yourself, you could take the derivative of it. Yes, you could definitely do that, but you know, my calculus is a bit rusty, and probably a lot of you, it would take a lot of work, right? So what we're going to do is a little bit easier than calculus on this. So you could take the slope of the tangent line at any point and you get the rate. But we are going to do something a little bit different, and that's the same as taking the derivative. We'll do something easier. Instantaneous rate. So that's the value of the rate at a particular time. It can be obtained by computing the slope of the line to the curve at that point. And obviously, again, this would be a lot more calculus involved, but I'll show you a much easier way. And then the second type of rate law, which we'll get into also, is called the integrated rate law, and it shows how the concentrations of species in the reaction depends on time. And this would be the integral of the curve, but we are going to, again, do this without calculus a little bit later. So let's focus on the rate law, or the differential rate law, if you want to say the whole mouthful. And it shows how the rate depends on the concentrations of the reactants. So again, for the decomposition of nitrogen dioxide, here's your equation. We would set up an equation called rate equals K is a constant, and it's found only by experimenting, times the concentration of the NO2 raised to a certain power. And again, this certain power can only be found by experiment. And this, again, is just your molarity. What they do is they look at the molarity of the reactant to start with, and they only focus on that, because they can watch that very carefully and monitor that, and they don't worry about the products. And so you get some sort of equation set up. And just to kind of give you another hint, let's just go back one last time. Well, just a pause, if you had two reactants going on, you'd have rate equals K times the concentration of one of those times the concentration of, the other reactant. So this only has one reactant, so that's why we say rate equals K times the concentration of NO2 raised to the X power. And so we have to determine X and we have to determine K. And that's going to be through a lot of experimenting and looking at the data, and we're going to do a lot of those number crunching at another time. But let's just focus on what is K and what is the rate. And again, we only look at the concentration of the reactants because we are not going to be studying any conditions where the reverse reaction does not contribute to the overall rate. So it's always a forward reaction, so you can't be reversed, and you're only looking at the reactants and how they're changing over time. We have to determine X experimentally. It cannot be written from the balanced equation. Those coefficients have nothing to do with it. And in summary, because we typically consider reactions only under conditions where the reverse is unimportant, our rate laws will only involve concentration of reactants. So I've kind of said that 3 times. Only look at the concentration of the reactants. And we get the information from experimental data. There's going to be different types of rates. You're going to have a 0-order rate or order reaction, a 1st-order reaction, a 2nd-order reaction, a 3rd-order reaction, and there is a 4th-order, but it's really rare. Usually you're dealing with 1st or 2nd-order reactions. Since that's what we want to decide, is what is the order? We have to determine the order by knowing those little powers, those little x's and those y's. And so that's what we have to define. And then it will also allow us to determine what K, the units on K should be. And they always start a reaction at T equals 0 or pretty close to T equals 0 as possible to get the best data. And they'll do this several times, using many different concentrations of each to get a really broad range of data. And then the results are compared to one another and calculated. And that's our kind of goal tomorrow. This is just giving you a little bit of prior knowledge. So here's the overall reaction order. The sum of the exponents in the reaction rate equation. So you have the reaction rate equation. So this is the reaction rate equation. It's going to be K times the concentration of A to the X power times the concentration of B to the Y power. Again, X and Y are not the coefficients here. You have to find those X and Y's by experimenting. And then you'll also find K by experimenting and taking the data and manipulating it and mathematically determining those. But what you can do then is, once you do find those, the X and the Y and the K, you will add together those little exponents, the X and the Y, and that will tell you the order of the reaction. And then K, you can also determine, like I said, from the experiments. So let's just say you get some rate equals K just times A, raised to the 0 power. This is called 0 order because, as you know, anything raised to the 0 power is just equal to 1. So your rate would actually be equal to K. If K was times A to the 1st power, that would be a 1st-order reaction. If K was times A to the 2nd power, this would be a 2nd order. And then let's just kind of expand. If you had 2 reactants and you were multiplying them and they were both, like, say, to the 1st power, then you'd add those 2 coefficients, the X and the Y, so it would be 1 plus 1 to give you 2nd order. This particular one is 1 plus 2 to give you 3rd order, or 2 plus 1 also gives you 3rd order. Again, you add the exponents together, and they are not equal to the coefficients. You actually have to solve those mathematically. And then the units of K depend on the order. And so this is going to require a little bit of messing around with the units. And I'm going to stop the podcast here because I can only go for 15 minutes. And we're going to talk quickly about how do you know the value of K. And more useful, like if I tell you K is molarity per second, you could tell me, oh, it must be a 0 order. Or if I told you K was 1 over S, you might be able to tell me that, oh, it's a 1st order, kind of an idea. And so that's what we'll talk about shortly.